Hello everyone, welcome back to Belmont's Math and Science Learning Center lecture series on Math 1240, Quantitative Methods of Business. This is Brandon Stevens coming at you from behind the camera. Since this topic is a little more Excel heavy, I figured just go straight to the computer rather than seeing my bubbly face at the whiteboard. Anyway, today's topic of conversation is Chapter 6, focusing on the transportation and assignment problems. The transshipment problems also talked about in this chapter will be covered in a different video. Anyway, transportation and assignment problems are very similar types of concepts, so we're going to be focusing mostly on the transportation part, but I'll throw in a few comments about how the assignment problems might differ. Transportation and assignment problems are just a very specific usage of linear programming. And so even though these Excel charts might look pretty different from what we've been doing up to this point, a lot of the concepts are going to be exactly the same. So hopefully as we go through this, some of the concepts that you've been working through for the last 3 chapters or so will start to come up and will start to help inform how you're going to tackle this particular problem. So let's go ahead and get started. I've got my question written out over here, so let's go ahead and go through it. We are tasked with sending computer parts from 3 manufacturers located in Los Angeles, Denver, and Houston to 4 different stores located in Topeka, Seattle, Nashville, and Orlando. Each manufacturer has a set supply at 200, 300, and 100 units respectively, and each store has a set demand at 150, 250, 200, and 200 respectively. Each shipping route has a set cost associated, found in the chart over here. How should we ship these computer parts to incur minimum costs? So this is kind of your textbook transportation problem. As you can see by this diagram I've got over here, you've got a set of origin points, kind of where you're building things or the manufacturers, those kinds of areas. And each of those cities or each of those locations have a specific supply associated with them. And they're sending out that supply to different destinations, each of which have a particular demand to satisfy all of their clientele. And it is our job to try and minimize the cost of sending along all those different goods to all of the different locations. So we might end up sending all of the 150 that Topeka needs from Denver, for example. Or we might send 100 from Denver and 50 from Los Angeles. It's going to be our job, using Excel, to figure out what the best combination is to try and minimize that cost. And so, as you can see, I've got this $60 here. That $60 just comes from this chart. Basically, it says, if we're to send 1 unit from Los Angeles to Topeka, it's going to cost us $60 to do so. So if we were to send 10 units, for example, how much would it cost? You got it, $600. So remember, this is just a complicated linear programming problem, so we're going to approach it from that respect. And remember, linear programming just requires 2 things. You've got your objective function and you've got your constraints. Let's start with the objective function. Our objective function is just an equation that models our goal. And our goal in this case is to minimize cost. And we know our cost has something to do with over here. So what our cost ends up being is going to be however much we send along the path from LA to Topeka times however much it costs to send things from LA to Topeka, plus however many items we send from LA to Seattle times however much it costs to go from LA to Seattle, and so on. You can do Los Angeles and Nashville and Los Angeles and Orlando. So what this is going to end up being is the number of goods found in these 12 multiplied by their respective costs over here and just added together. So what we can do is this handy little trick with sum product. And I'm going to go ahead and highlight these blanks, which is just going to be however much is sent on these paths. And I'm going to put a comma and then I'm going to highlight those prices. And I'm going to hit enter. And good, it has 0. So what we've just done is, instead of doing this blank times this number plus this blank times this number, we just did sum product. And that's our objective function. So now let's talk about the constraints. And the interesting thing to deal with in a transportation problem is these constraints. And it all goes back to whether this is going to be a balanced problem or an unbalanced problem. Essentially, what you have to watch out for is, what is your total supply compared to your total demand? So you can kind of see here, you got 200, 300, 100, that's 600. And you got 150, 250, 200, 200, that's 800. And what I recommend you do, because you have those numbers in your chart over here, is I recommend just like off to the side somewhere, you can do total supply and just add up all of these supply numbers. And for total demand, do the same thing. Add up all of these demand numbers. Your charts are going to be laid out basically the same way. And so if you just take the time to set up this little chart, it really helps out in the long run. So anyway, you can see plainly that the demand outweighs the supply, which means no matter what, even if we sell, or even if we send out everything we have in our manufacturers, some of our customers are not going to be satisfied. Some of our customers are not going to be happy. We're not going to be able to meet all of our demand. And what that ends up meaning is our demand constraints will be less than or equal to, our supply constraints will be equal to. And I'll explain that kind of in a second. But the big thing to remember is the bigger number, whatever that's associated with, those constraints are going to be less than or equal to. So let's go back to this chart. We already know that these 12 blanks are just how much is sent on those paths. The shipped from is going to be the total that is shipped from Los Angeles. So you can just do sum of the row. And the same thing with shipped from Denver. We can just do the sum of the row. And if it helps, you can just kind of drag that down because Excel is nice like that. The shipped to means everything that is shipped to Topeka. So we're going to be sum of the column for Topeka. And just for ease, we're going to drag that all the way over. Now our chart is set up. So as we do, we are going to go to data and we're going to go to solver, just like all of our other linear programming problems. So remember, first blank, that's where our objective function lives. It's already on B8. That's where we want it. Our goal is to minimize that spot, so we keep it on min. Our variable cells in this case. Our variable cells are going to be how much is sent on each path. So we are going to highlight the 12 blanks over in our chart to the left. That's going to be the numbers telling us how much is sent on each path. And then we've got our constraints. So remember how I said supply was equal, demand was less than or equal to. So what that means is our 3 shipped from are going to be equal to our supply numbers. And essentially what that means is we are going to send out everything that we have. So this 0 better be 200 at the end of this. This 0 better be 300. This 0 better be 100. That's kind of what I mean by that. And now our next constraint. That's going to be the demand. And demand in this case is going to be less than or equal to. So our cell reference is always going to be shipped to. And our constraint will be the demand, which means the shipped to Topeka is going to be less than or equal to the actual demand for Topeka. We might not actually meet the demand. We're going to try to, but we might not be able to. Boom. And that is our constraints. It is important to note, always do the shipped from and shipped to before you do supply and demand. That cell reference should always be the shipped column. Otherwise, you will probably make a mistake, and it will tell you there is no solution, but there will be. There should be a solution. Make sure this box is checked because we want non-negative answers, and keep that at simplex LP, and we hit solve. And there we go. Solver has found a solution. Always make sure that Solver has actually found a solution. You don't want to not actually have a solution. If it says you have not found a solution or there isn't a solution, you probably need to check your constraints. You probably switched your equals and less than or equal to or something to that effect. But there we go. And that's basically our answer. So we can see that Topeka got slighted. Only 50 things actually made it to Topeka. Also, Orlando got slighted. Only 100 things out of the 200 actually made it. But you can kind of see, okay, 50, Denver sent 50 things to Topeka. Denver sent 50 things to Seattle. LA sent 200 to Seattle. Denver supplied all of Nashville, that kind of thing. And the total cost came out to be $22,000. That is our solution to our transportation problem. It tells us exactly how we should ship our materials and exactly what cost we're looking at in the end. Now, one more thing I didn't mention about the constraints. If these turn out to be equal, like if this was 600 and 600, then that would be what we call a balanced problem. And in that case, both of these are going to be equals. But since it's an unbalanced, one of them is going to be equals, one of them is going to be less than or equals. And there you go. That is how you handle a transportation problem. Assignment problems are exactly the same concept, but all of these numbers that are going to appear in here are either going to be 0 or 1. You can kind of think of the suppliers as maybe different people that are being assigned to different tasks, or maybe different locations. Maybe they're referees sent to different sporting events, and we want to minimize the cost of the travel. So one person can only go to one place at any time, and that's why it's just going to be a transportation problem, but with only zeros and ones in our decision variable blanks. But there you go. That is Chapter 6 on transportation and assignment problems. Hopefully you learned a little something here, and wish you best of luck. Thanks so much.